In quantum physics, electrons are fundamentally wave-like, lacking precise positions, yet, in many contexts, like explaining electrical conduction, they can be effectively described as classical particles with specific speeds. This particle picture underpins even advanced concepts like topological states of matter, recognized by the 2016 Nobel Prize, which rely on assumptions of well-defined electron motion. However, researchers at TU Wien have now demonstrated that this particle-based view is not essential for topology. In extreme quantum regimes, electrons can lose all particle-like characteristics, yet topological states persist. This finding challenges prevailing theories and reveals a more universal nature for topological phenomena. The breakthrough centers on a compound of cerium, ruthenium, and tin, CeRu₄Sn₆. At temperatures near absolute zero, it enters a quantum-critical state, fluctuating intensely between two distinct phases. In this regime, charge carriers are so delocalized and correlated that the quasiparticle description, the idea of electrons as individual entities with defined velocities and energies, is thought to break down completely. Paradoxically, earlier simple theoretical models, which ignored this non-particle behavior, had predicted this material should host topological states. Topology, borrowed from mathematics, classifies shapes by their invariant features. A bread roll can be deformed into an apple, same topology, but not into a donut, which has a hole. Similarly, topological states of matter have robust electronic properties protected against minor disturbances, making them promising for quantum computing, lossless electronics, and advanced sensors. Faced with the contradiction between theory, predicting topology, and the expected physical behavior, no well-defined particles, the team pursued experimental verification. At ultra-low temperatures, they observed a spontaneous Hall effect, a deflection of charge carriers, without any external magnetic field. This signal is a hallmark of topological states. Strikingly, the effect was strongest precisely in the quantum-critical fluctuating region where the particle picture should be invalid. When fluctuations were suppressed by pressure or magnetic fields, the topological signature disappeared. This result was pivotal. It proved that topological properties can exist independently of particle-like behavior. The researchers, collaborating with theorists at Rice University, identified the phase as an emergent topological semimetal. They developed a model linking quantum criticality directly to topology, showing that the topological distinctions emerge in a more abstract mathematical way. Intriguingly, the experiment suggests topological properties may even arise because particle-like states are absent. The discovery has profound implications. It expands the fundamental understanding of topological matter, showing it must be defined in more generalized terms, not tied to the paradigm of well-defined particles. Practically, it opens a new pathway for material discovery. Since quantum-critical behavior occurs in many material families and can be reliably identified, scientists can now systematically search for new, emergent topological materials within these systems. This connection could significantly accelerate the development of next-generation quantum technologies. In essence, this work bridges two previously incompatible concepts, topology and quantum criticality, revealing a broader universe of topological matter. It demonstrates that even when electrons stop acting like particles, the robust, useful rules of topology still apply, guiding physics toward novel and potentially transformative quantum materials.